The following static charges with a magnitude of q are positioned in a square configuration at a distance d from each other. And part A asks us to draw an equipotential line along which the electric potential is 0. Well, if we start by looking in the middle of the electric field, we can visualize that the radial distance of the negative charge is equal to the radial distance of the positive charge from this point. So if we compute the potential at this point, what we're going to have is 1 over 4 pi epsilon naught multiplied by the negative charge on the distance to this point, which I'm just going to call L, and then plus the positive charge 2 over L, and then plus the positive charge 3 on L, and then plus the negative charge 4 on L. So as we can see, the negatives will cancel with the positives, and we end up with a potential of 0. Now if we look at this point over here, we can also observe that the radial distance of this negative charge 1 is equal to the radial distance of negative charge 2 to this point, and similarly the radial distance from charge 3 to this point is equal to the radial distance from charge 4 to this point. So that's also going to give us a potential of 0. So we can observe that the equipotential line along which the electric potential is 0 is this horizontal one over here. Now part B asks us to find the total potential energy required to assemble these charges. Well, what we have is the total potential energy is equal to 1 over 4 pi epsilon naught, and we multiply this by the product of charges on the radial distance. So if we start off with charge 1 and charge 2, well, the electric potential energy contribution to assemble these two charges is minus q multiplied by q over the distance between them, which is d. And now if we bring in another charge 3 into the electric field of charge 1 and 2, well, we add the electric potential energy contribution due to the interaction between charge 3 and charge 1, so that will be minus q multiplied by q over the distance between them. So by Pythagoras' theorem, that would be the square root of the horizontal distance squared plus the vertical distance squared. So that would be 2d squared. And the electric potential energy due to the interaction between charge 2 and 3 is effectively q multiplied by q over the distance between them. And if we now place charge 4 in the electric field of the other three charges, we have minus q multiplied by minus q due to the interaction between charge 4 and 1 over the distance d, and then plus the interaction between charge 4 and 2, so what we get is q by minus q over root 2d squared, being the radial distance between charge 2 and 4, and then plus the interaction between charge 3 and 4, which is q by minus q over d. And now if we simplify this, what we get is 1 over 4 pi epsilon naught, and this term cancels with this one, and positive q squared minus q squared, we're going to get a cancellation between these terms. So what's left over is negative 2 by q squared over root 2 by d. And we can simplify this a bit further. So what we'd get is minus q squared over 2 root 2 by pi epsilon naught d. And now we're asked if a test charge plus q is placed at the center of the square and released, find the kinetic energy when it reaches the midpoint between charges 1 and 4, which we'll call point A. So recall that the change in kinetic energy is the negative of the change in potential energy. In this case, we're looking at electric potential energy. And remember that the electric potential energy was equal to the charge by the change in electric potential. So in this case, we have the final electric potential minus the initial electric potential. And we know that along this equipotential line, Vc is 0. So we end up with minus Q by VA. So we can calculate the electric potential at point A and multiply by negative Q. So we have minus Q multiplied by 1 over 4 pi epsilon naught, which I'm going to factor out, and we multiply by the contribution of the electric potential due to the electric field of every one of those charges. So for charge 1, the electric potential is minus Q over the distance to point A, which is d on 2. And then plus the contribution of charge 2, so that will be Q over the radial distance from charge 2 to point A, so that will be the square root of d on 2 squared, which is the horizontal distance, and then plus the square of the vertical distance. And then for charge 3, we have a similar result, so that will be plus Q over the square root of d on 2 squared plus d squared, and then the contribution of charge 4, that will be plus negative Q on d on 2. And this here is the change in kinetic energy of the test charge. And then doing a bit more simplification, we have minus Q on 4 pi epsilon naught, and Q on d on 2 is 2Q on d. So what we have is minus 4Q on d, and then the sum of the second and third terms gives us plus 2Q, and if we factor out d squared, we have over d by the square root of 1 on 4 plus 4 on 4, which is 5 on 4. And now if we factor out Q on d, what we get is minus Q squared on 4 pi epsilon naught, and then we have negative 4, and then plus 2 in the numerator by root 5 on 4, so that gives 4 in the numerator over root 5. And we can do a bit more simplification, so these 4's are going to cancel, and what we get is positive Q squared on 4 pi epsilon naught multiplied by 1 minus 1 on root 5. And we can see that the change in kinetic energy is greater than 0, because there's a decrease in electric potential from point C to point A, so which gives an increase in kinetic energy.